Hi, in this video we're going to talk about how to stretch graphs horizontally and also reflect. So in this case we may be given a function whose graph is given something like this, say. Okay, there's my function, say g of t. So in this case the independent variable is going to be t. What we want to do is figure out what does g of 2t look like. Well, anytime we work with the independent variable, things go backwards from what you might be used to with the independent variable. If we'd multiplied the outside of this function by 2, so if we multiply the 2 out here, then what happens is we stretch by a factor of 2. When you multiply the independent variable inside the parentheses, then what actually happens, we don't stretch horizontally by 2, we stretch by 1/2. So we actually shrink the graph. So the reason being, and so I'll just give a brief explanation and then we'll just think about the general principle. Suppose I'm at this point here. If I want to understand what g of 2t is, well, if I start with this being t, then twice this value is out here. So here's g of 2t. So what happens for the new function, let's call that new function f of t. New function's f of t. The value of f of t at this particular t is the same as the value of g of the function g at 2t. That's what this says. The height of g at 2t is here. So what we have to do is the height for f is the same as what it would be at 2t. So the height above for f is here. So this is the value of f at t. Okay? If we're actually at 0, nothing really changes because 2 times 0 is 0, so they're the same. But what if I'm over here? Suppose I'm at this value, and this is my t. Then what I want to do is take twice that. So this is 1, 2, 3, minus 3, minus 6. Look at the value of g at this particular point. So this is going to be 2t. So this height, this negative height, will be g of 2t. This is going to correspond to the f value at t. So this height should be the same as this height. Okay? So I have these 3 points that are on the graph of my new function I call f, which is also called g of 2t. So that graph looks something like this. See, it's been shrunk inwards towards the y-axis by a factor of 2. In other words, it's been stretched by a factor of 1/2. Okay? So the general rule, this is what you should remember, hopefully you've been convinced, is that the graph of f of k, where k is some positive integer, k times t, or x, might as well say x, is the same as the graph of f of x, but stretched horizontally by a factor So in this particular case, k was 2. And I'm assuming here k is positive. So if k is positive, in this case k is 2, the graph of g of 2t, which is this orange graph, this is the same as the graph of the original g, but stretched by a factor of 1 over 2. That is 1 over, if k is 2, it's 1 over 2 by 1/2. So stretching by 1/2 means I shrink, and I'm shrinking in the horizontal direction. Again, just as in vertical stretching, the intercept, in this case the y-intercept, is not changed. Everything gets stretched or shrunk towards the y-axis. Okay, so how could I actually stretch in the horizontal direction by a factor bigger than 1? Well, use the same principle, but you choose k to be a fraction. For example, let's look at a similar graph. Okay, there's my function. I'm going to call it g of t again. And there's my independent variable t. And now what I'd like to do is actually stretch, but by a factor bigger than 1. Well, then what should I look at? For example, if I want to stretch by a factor of 2, then I claim that what I use is g of 1/2 t. So g of 1/2 t means stretch by 1 over 1/2. So k here is now 1/2. This is my k. But 1 over 1/2 is the same as 2 over 1 times 1, which is the same as 2. Okay, so since I put a 1/2 here, I have to take the reciprocal. That tells me the stretch value. So here k is 2 means I stretch by 1 over k, the reciprocal, which in this case is 2. So what does the graph look like when I put this factor of 1/2 in? Well, it looks like this. It's stretched. Nothing changes at the y-axis, but x values that are very far away from the y-axis are disproportionately stretched, or proportionately stretched, if you like. So what's the graph of this function? It's g of 1/2 t. This is the graph of g of 1/2 t, or in other words, another way to write that is just g of t over 2. Okay, so dividing by 2 or multiplying by 1/2 means you have a longer graph in the vertical direction. Okay, finally I want to comment on what happens with negative values. So in this case, k was 1/2. In the previous example, k was a factor of 2. What if I do something like negative 1/2? What happens in that case? So if you put a negative number, so now let's look at negative 1/2 t. Not only do you have to stretch by a factor of 2, because we have 1/2 here, but we also have to flip. But we're flipping x values. We're changing x values here in this case. And so all the x values get moved across the y-axis. So for example, here's a x value of say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, negative 11. That will go off to a positive value of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that goes off 11 here. Okay. And so now that means that this value goes over here. A value here, for example, for g of 1/2 t, would go over to here. So everything gets flipped. So across the y-axis. So now the new curve will look instead something like this. So this is going to be the graph of g of minus 1/2 t. It's the same as the yellow curve, it's just been flipped across the y-axis. Okay, that's completes our discussion of stretching in the horizontal direction and also flipping in the horizontal direction.